Hello, welcome to another coding session. More Bangalang, more Bangalang. But now we're finally getting into some multi-threading, which I keep promising. I've been promising forever. What I want to do today is I want to create some primitives for multi-threading to help us communicate between threads. So I want to make atomic integers so we can increment and decrement some integers atomically, which is to say that other threads cannot interfere during the increment and decrement. I want to create a semaphore, a counting semaphore, and I want to create a mutex. Those are the three things that I want to create. And we'll do a little bit of improvement to our thread handling, which is super basic and is still going to be super basic, but let's make it a little bit better at least. So, where do we want to start? I think the easiest place is an atomic integer. So let's say blah atomic I64 equals 1. We should be able to do like blah plus equals 3 and exit with blah. We're probably going to have to do untyped just to keep my type system happy. Like eventually we want to do some better type conversion as well. I mean, an atomic I64 is basically just an I64. It's just that internally my language is going to handle it a little bit differently. But I mean, conversion between atomic I64 and I64 should be like no big deal, you know? As always, we need to make sure that things are pretty. That's really important, so we'll do that first. If we get all of these I's, like so. And we'll go atomic. So we're going to have atomic variations of all of the integers. There, now we get a nice color. Okay, so this is the first thing we want to implement. So this should exit with code 3. 1 plus 2 is 3. So let's try that. We don't have any new tokens. We don't need to do any tokenization stuff. Parsing. I don't think we even need to. No, well, parsing. So actually, no, I'm wrong. We do have a new token, plus equals. And I also want to add a minus equals. So that will be in tokenization. So we're going to have like plus equal, sorry, that'll be here. And minus equals. And did I do that right here? Minus equals. So I feel like I did that wrong. It should be like that. Okay. So that's that. And then in parsing, we can add these. So what precedence do they get? Let's defer to Odin. So he doesn't actually have them in here. Which is interesting. He says unary operators have the highest precedence. Does he mention anything about, like if I say plus equals, I look for some uses of that. Because I feel like it should have a higher precedence Actually, maybe it should have the lowest precedence. I don't know. I really don't know. So we're just going to put it in here for now. But I think we're going to have to do something better than this. Because what if we have some code that's like x plus equals 1 plus 2, 1 plus 3, right? We don't want to evaluate this first. We want to evaluate this last, right? We want to do this first and then this. So by making these the same precedence, this is going to happen in the wrong order. Which is why I thought maybe this should have like the lowest precedence. So this comparison, yeah, it's interesting that he didn't even put it in his precedence list, I don't think. No, I don't even see it in here. So maybe it's like some special other thing. I'm just going to do it like this for now because it's easy. But I think we're going to have to do something better at some point. So plus equals is like add add a sign, I guess. Let's call it add a sign. So minus equals will be subtract a sign. Like so. So that takes care of that one. And that one, what about this one? They are binary operators, so we need to add it to this list as well. Like so, and this doesn't really need to be, yeah, it's a bit weird. Really, I could just have like a list of binary operator ones and then check whether it's in the list. Maybe that's better. But let's just leave it like that for now. So I think that handles those new operators. Now in type checking, is there anything new we need to do? Well, I think what we're going to do is I'm not going to allow I don't really understand this stuff very well, but I think I'm just going to not allow the atomic ones to do regular like plus, minus, multiply, divide. I'm only going to allow plus equals, minus equals for now, because I'm going to do some special assembly that is atomic for those. So for now, that's all I'm going to allow them to do. So when I'm type checking a right-hand side expression, there are some checks in here. So we're making sure it's a numerical type. I guess we need to extend this actually. To add the atomic ones. And we'll also add it to... So I guess instead of adding it to signed integers, let's make a new atomic integer list. And we'll handle those separately. Then down wherever we were, here. So we're checking whether it's a numerical type. If it's not a numerical type, then that's a problem. And check if it's an atomic integer type. So if it's not, so if it is an atomic integer type and so atomic integers, we should be able to do comparisons. So we know if it's a comparison operator already, we can use that. So and not comparison operator, and it's not add a sign, and it's not subtract a sign. That's what we're going to allow comparisons and those two with our atomics. And we'll just keep this shitty message. The messages are so bad, but we'll just keep them for so far. So that, I think that's it for that. And the generation is where things get interesting. So we should have, yeah, here's our signed integer code. So I'm going to make an atomic integer as well. Let's put that up above. So this is atomic integer. And we do all the comparison stuff is all exactly the same. But we have add a sign and subtract a sign, and we don't do any of this stuff. And we just need to make sure that this is all good. So the result location is not copied to register because we want to maintain it. It's actually just left-hand side. Yeah, whatever the left-hand side was, that's the location. And I think because that's probably going to be a memory address, if this is a memory address as well, then that's a problem. Because at least with the assembly that we're using, x86-64, you can't have an add with two memory addresses. So I'm going to make sure that the right-hand side is in a register. I'm going to put +1 here. That actually reminds me that I realized that something we can do to simplify things is we could just do this, I think. I don't think we need to keep going further. Like I did have all this complicated math here, which basically meant that the deeper you get into an expression tree, the higher the register numbers get, so that we don't conflict with registers that we've already set. But I think it was a bit overkill, and I think this will be enough. So, but yeah, so the right-hand side should be a +1, just like this, you know? Just make sure that it's a +1. Otherwise, we're going to get conflicts between the left and right-hand side. Yeah, that looks right. So we make sure that's a register, and we add it to the left-hand side, basically. And we return the left-hand side. So that's how you do plus equals, I guess. Well, actually, that is how you would do plus equals for the regular integers, right? So let's go like this. Yeah, I guess it would be like that. So let's go back up and get the subtractor sign, like so, and put the right-hand side register there. So that's going to handle add a sign and subtract a sign for integers. We haven't implemented it for floats, actually, and I'm just going to ignore that for a while for now. We'll get an error if we try to do that. So now the interesting thing here is how to do it in a atomic way. And we use lock xadd. I'm going to call that atomic add. There's no sub. There's only xadd. So what I'm going to do here is, before we do xadd, I'm going to negate. I'm going to negate the right-hand side. That's not right. I think we just go like this. Yeah, I'm going to negate the right-hand side before adding it, so that'll effectively subtract it. So I think that's about it. That should be our atomic operations. What happens if I run that? Get a good old segmentation fault. All the stuff above it is commented out, so let's have a look at what we get in our assembly. So we allocate 8 bytes, that's a 64-bit integer. We copy the number 3 into it, which is already feels wrong. And then it's like we add 2. And then we subtract 4. This is all wrong. I think this is actually some old assembly because I was playing with this before and it looks like the old assembly. Yeah, so it's actually in the compiler that we have issues. So we're trying to do an assignment. The left-hand side node is blah, and it's not happy. Why is it not happy during type checking? The node is blah. And it thinks that it's a struct member. That's interesting. Why would it think that? It should not be coming into here. And what is child node? Atomic I64. Identifier. Ah, I think I know why. I know why. It's because this is not getting converted to a type. We need to add them in here. It doesn't realize that it's a type. So now it's in our list of types, known types. So it should get resolved to a type now. We still get a segmentation fault. Oh, we have a loop going. So what's the node? The node type is add assign. So I think I know why. It's because we have this binary operators list. And we need to have add assign and subtract assign in it. Okay, incompatible types, line 188. Yeah, that makes sense. I don't know why that was like that. Shouldn't it be like that? Unsupported byte size. Again, that's probably because we have this list of sizes and for different types. So we need to make sure the atomic guys are in here. Failed to generate expression. Let's see why that is. Oh yeah, we never added it in here. So this is where we're generating expression. We need to figure out that it's an atomic integer and call the atomic integer procedure. This is the one that we just created, right? We just created this procedure, but we never called it anywhere. So now we do. Okay. And we have exit code 3. So 1 plus 2 is 3, and we exit with 3. Great. If I plus equals 4, then minus equals 2. We should still have 3, which we do. Great. So I think that's all we really need for atomic integers. We know that, I mean, if we look at the assembly, we can see that it's doing the, like say this second one's doing a negate. So it should be all good. So the next thing I want to do is a semaphore, which is basically just a way of using the atomic integer. So semaphore wait is a procedure that takes in a semaphore, which is a pointer to atomic, I don't know, let's call it I32 for now. And it's just going to loop forever. Well, not forever, we'll get to that. Unfortunately, for me to add a return into a procedure, I have to have a return type. I need to do something about that. So we can say, like, the semaphore, we dereference it, and then we minus equal 1, so we decrement it. And if the result of that decrement is greater than or equal to 0, so we didn't go negative when we decremented, then we return. Otherwise, we increment again. So we like undo the decrement. So what that effectively means is that when we're waiting for the semaphore to be above 0. As long as it's 0 or lower, we're just going to keep spinning, because when we decrement, the result of our decrement is going to be less than 0. So it's going to keep coming in here. But then if any other thread comes along and increments the semaphore up to 1 or higher, then when we do our decrement, we should end up in this else. Oh no, sorry, what we would, when it was 0 or lower, we would go here, and we would just undo the decrement. But then if another thread comes along and increments the semaphore, then we'll finally come into here and we'll exit. And the increment of the semaphore is basically called signaling. So basically all that is just incrementing the semaphore. So one thread will wait, and then another thread will signal, which will mean that the thread that was waiting can stop waiting. That's the idea. So we can test that. So if I go semaphore atomic I32, and then I go semaphore wait, then we should see semaphore test complete. You can put some comments. So we should see this get printed, but this should never get printed because we should wait indefinitely because we're never signaling the semaphore. But instead we get an issue in the standard lib at line 39. What is the issue with that? Line 39, column 61, that's here. Procedure has no return type. Because I'm putting an expression here, and I think usually in our type checking that would get wrapped in a return node. Is that right? So that'd be, I think that's in type check assignment, not assignment, statement. Type check for if type check statement. Or maybe it's generation of a statement. No, it shouldn't be that far. It should be in type checking. So it's obviously not in here. Is it in the assignment stuff? Here we go. This is where we wrap in a return node. And I guess we want to say, like, maybe if we type check the statement first so we know what the right-hand side node type is. And then if get type, I guess it would be get type result. So RHS type result. Is that kind of naming convention I was using? Node result. If that's not nil. Because if it's nil, then there's no point in wrapping it, right? It's just a right-hand side expression. And that should be fine. Yeah. Cool. Or is it cool? Oh, we need to get rid of that so that it actually does this test. Okay, so we see semaphore test, and it never gets to semaphore test complete because we're waiting forever. That makes sense. If we do a signal first, which basically just increments our semaphore, then we should exit straight away, which we do. Now the next thing, because the whole idea of this is that we want to do it on another thread. Right, it's a multi-threading thing. So we need some way to get our semaphore into another thread. And right now we can't do that. This is our clone. I'm going to change this to start thread because it does a little bit more like this part here is the actual clone, but it does some other stuff around it. So I'm going to change it to a different name. Let's go to type checking first where we define it. So that's here. Maybe I'll just do a replace, rename, code occurrences, yes. Start thread. So what I want to do is add that there. So we have a second parameter, which is oh no, so actually it needs to be like this. And I think there needs to be a 1 now. This defining these gets so complicated. Oh, so that's arg, and that's I64. So our start thread procedure now has 2 parameters. One is the procedure that we want the thread to start, and the second is an argument we want to pass into that procedure, which is an I64. So we also need to add that as a parameter in this procedure. Let's see if we can manage that. So I guess that's like a child of that. And then that's even a child of that. Jesus. Yeah, that shit gets hairy. Oh, and that should be a start thread. So let's try that. So now the start thread is taking 2 parameters. So let's put this one in RCX, which is another register not being used. And this one will get bumped back to 16. So this is still the first parameter, which is the procedure we're calling. So that's why we do this. This one here is the argument, RCX. So what I want to do now is actually copy RCX into the stack. So this here is it's a bit basic right now. We just have one stack, which is just defined in our BSS section. So it's just like a static. There's only one, we can only have one thread at a time. If we have multiple threads, then this is going to be used for each thread and it's just going to create a whole mess. So we need to change that at some point. But here we're going to the end of that thread stack space. Then we're coming back 16 and we're putting our parameter there. The reason we're coming back 16 and not just 8, since this is only an 8-byte thing, is to maintain our 16-byte alignment thing. I think that helps. Let's see. So now also what we pass in as the stacks of the thread, we're going to say the stack pointer is also at -16, because that keeps them with our calling convention. So that means that the first parameter will be at the top of the stack when we first go into the procedure. Okay. Another thing I want to do is add an exit here. So this will cause the child. So the child will come in and do this stuff. It will call the procedure, and then when it comes back, it'll just exit. So that the child thread will exit. The parent thread will jump here. It'll jump down to the end and then return. I think that's right. We might have to play with these flags also, but let's leave it for now and see if it works. So now the idea is that we should be able to go like semfunc is a proc which takes an I64 and just signals the semaphore basic. Well, first we have to convert it to a semaphore because our argument is just an I64. So semaphore equals the untyped arg, and that's a pointer to an atomic I64, like that. And then when we do our start thread, we pass in the semfunc and the semaphore, which we're going to have to say untyped again. So this untyped stuff is really hacky. But right now, the reason I'm using it is because start thread expects the argument here to be an I64, but we're passing in a pointer to a semaphore, which is also a 64-bit value, so it works. But the types are different. Like this is a pointer type, and this is just an I64 type. So here I'm just saying ignore the type and just pass it in as an I64. And then when we come in, now I'm saying, okay, ignore the I64 type and let's go back to what it actually was. Oh, it needs to be I32. And then, so hopefully we will start this thread and then this will wait, but then this thread will signal, which will mean that we can go to here. Let's see what happens. Index out of range, okay. What's that all about? Okay, I think that needs to be a 0. I think this one needs to be a 1. Yeah, because this line we add to these children, and then we do stuff on that first child. Then this line we add a second child, and then we do stuff with the second child. I think that's right. Cannot reference type atomic I-32. Okay. I think that's right. So I think that means we don't need to do that. Right? That was on line number 191, because this is already a pointer. So we don't need to reference it again. Okay, it seems like this has never been called, maybe. Yeah, we're not getting signaling. Okay. One thing I'm going to try here, because I have had a look around with Grok doing some research. And he did give a suggestion of some different flags. I think it was like 10D00, which was like this combination of flags to the clone. So if we change this, and it's like 10D00. Yeah, 10D00. I think I had better luck with that. Segmentation fault. Okay, so that did not really help. If I take away the start thread, okay, then we don't have any issues. What if I take away the contents of this? Okay, segmentation fault. So it's not to do with the content, it's to do with the start thread. Somewhere in here there's an issue. Let's, just to be extra sure, let's comment all this stuff out. Maybe comment that out. Comment that out. Okay. So it was all good, but then start thread caused issues. So here's start thread. Okay. Why? So let me go back here. It's putting the parameters into RDI and RSI, which is the convention for extern. Yeah, it's marked as extern, which is wrong. So this should pass the parameters better. Okay, so we got rid of the issue. So now it's passing them. See, now it's passing them onto the stack, RSP plus 8 and RSP. That's what I would expect. And that's what this code here is expecting, right? It's expecting them to be on the stack. The reason this is 16 and 18, even though this is 8 and 0, is because once you go into the procedure, there's actually the instruction pointer, which also goes onto the stack. I have this visualized somewhere here. Probably here. Yeah, once you get into the procedure, here's the start of the procedure. It's kind of in here, and then you have this instruction pointer. So then this is all the stuff within the procedure that you put on the stack. But this needs to be here so that when you go to return, at the end here when we do return, it needs to know where to return to, and that's what this instruction pointer is for. Okay. So that was promising. Let's actually do the signaling, see if that works. Okay. Cool. Let's go 2. So it didn't get past there. We need to signal again for it to get past. And it works. Okay, I think that's good enough. I think that's our semaphore sorted. Now the next thing I wanted to do was a mutex. And for a mutex, we need to use, was it like compare exchange? Compare exchange. Let's go down, find the example of using it. Where is it? It talks a lot about it, but here's the example code. Compare exchange, like this. This is it. So maybe I just implement this assembly and then we'll figure it out together. We can then figure out what it actually means. So first, because I'm going to hard code this, we need to tell the type checker about its existence. Compare exchange. I don't think it returns anything actually, so let's take out the return value. Let's take those out. So like that. It seems like it's even thread proc. Yeah, I think it's even like this. There we go. So compare exchange needs to take in 3 arguments, I think. The value, which is actually a reference to, let's say, an I32. Then we need an expected value. And like a replacement value. And I'll explain what all this is in a minute. Okay, so I think that defines it. Then over here we can get the assembly for it, which should look something like this. JC done. I think we just have this return, which by convention generally has a dot end. Although I think in this case we don't really need a dot end. So let's just return afterwards. And that's a move. Okay, so how does this work? We put our expected value in EAX. So the expected value was the second parameter. This was the last parameter as the desired, or the replacement value. That's what we want to assign. So this here, let's start with this one actually. This is RSP plus 81624. So this is the first parameter. This is the value. right? This is the value that we pass in. And it will check, it'll compare this value to our expected value, which is the next parameter. Let's put copy, copy. That's enough. Yeah, so it will compare what's already in our variable, our value, to our expected value. And if they are the same, then it will update this value to be whatever this value is. So let me put it in code, how it will look. So if we say like foo is an I32, and then we say compare exchange foo with 0 and replace with 1. Let's make it a nice, I think this could give wrong values, but if we did something like this, I don't know if it's actually going to work. No, it's not. I mean, the idea is that we have foo, which is a 0. We compare it to 0, and because they're the same, then we will assign 1 to foo. That's how it works, and it's an atomic operation. So we have this lock. It seems like it did not work. And I'm not sure why. We might need to reference, because this just has an address in it. So we might need to dereference. Maybe. Does that make sense? Because this is holding an address right now. Where futex word in this context is holding what? I think it's just something from, I think it's just in their code, they just put it like up here or something in the data section. Yeah, like futex word is a double, so it's like 4 bytes. Yeah. So what's the problem here? Let's go in here, semaphore wait. Print line, where's the compare exchange? Is it not even getting to there? Okay, so there's a problem in here. So the param node variable is not available. Okay, so params type node has children. the value is value. I guess we did have. Yeah, I guess that's right, actually. We called it value. Yeah, it's value. Okay, value is value. And it has a child, which is reference. And then that has a child, which is I32. So reference to an I32. But this type node is null. Oh. Ah, but I think I need to do this. This one, so this one did not have a type. There we go, so we get exit code 0. Which according to my understanding is wrong. Foo should be 1 after compare exchange. So it's calling compare exchange. And then exit. So the one thing I'm still a little bit confused about is in here in my compare exchange, like this is holding an address. So I do feel like, let's say RBX, let's try this again, RBX, and we put RBX like that. It didn't fail, but it didn't succeed either. Maybe I need to be loading the effective address. I'm sure that should be, I'm sure the idea is that you take that and you replace that. So we dereference the initial one. Because RSP plus 24 is holding an address. So now the address I think if we look at dereference in other places, yeah, it's just a move, but then it's treated. Yes, this is the same thing, right? We dereference, then we use it. So I feel like it should be the same as this, basically as this. The semaphore wait, because it was pointed to a semaphore. And here again, we're taking a pointer to an I32. So that's the comparison, 8, 16, 24. Oh no, these are, I'm so used to using 64-bit. This should be like 12 and this should be 16. Because each of these things are only 4 bytes. 8, 19, 11, 12, 13, 14, 15, 16. Okay, now it's exit code 1. Right. So so it's compared those with those, seen that they're both 0, and then assigned 1 to foo. So if I go like this, now foo is 0, it's expecting it to be 1. They're different, so it should not set it to 1, and this should just be 0, which get exit code 0. Okay. All right, so we're making some progress. Now the next thing, maybe the last thing we'll do in this video, is that I wanted to make mutex. which is why we needed this compare exchange, because it uses it. So, and it's also going to need a new system call, which I think we have in here. Futex, where are we? Let's find where it's used. Futex log. I wanted an assembly. Okay, I think actually maybe yeah, where's like this? Here we go. Here's an example of doing the Futex stuff. So it's a syscall with 202. So that's what I was trying to get at, is I want to have this syscall implemented. So it's called Futex, which I think is like fast user synchronization something something. So we'll pass in a pointer to an I32, and it was syscall 202, and this Futex word, the address of the Futex word is the first parameter. So that's this. I'm going to do untyped to convert it to an I64, because that's what syscall is expecting. The expected value. So first we're going to say a Futex wait, because when you call the Futex syscall, there's like a few different operations that you could do. Well, actually, that would be like, we're not defining which one we're calling yet. So that would be the operation and then the operation can have a couple of arguments. And that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I guess we need to add a couple of zeros on the end. I don't think there's anything else we need to pass in. Oh, there's a timeout. Oh yeah, but these are the two arguments to Futex wait. So now we can do like mutex lock, and we pass in the mutex, which is just a pointer to an I32, and that's going to call Futex with the mutex. The operation is 0, which is Futex wait. Well, actually, it's like first we're going to do compare exchange. If compare exchange equals 1, does compare exchange have a return value? We don't seem to be returning anything. So maybe we didn't do a compare exchange, and then depending on what the result is, So we do compare exchange with the mutex. We're expecting it to be 0, which I'm calling unlocked. And if it is unlocked, then we lock it. We set it to 1. I do think that there is like... I do think there is a way... Well, I could just do lock inc for the plus equals minus equals. What are we looking for? I wanted to have a look again at this this compare exchange business. Yeah, so J0, yeah, if semaphore equals EAX set to ECX, and if it's successfully decremented, we do this. So I think what I want to do is have a return value. And you can do like a set Z. So RSB plus 8. So what I want to do here, so the return value is, oh, my calling convention. I think it would be there actually. I think the parameters, it's further back from the parameters. So after this, see here they're using jump of 0 and they're saying they were successful. So the 0 flag is set if it was successful. And here I'm saying set if successful, which is basically setting like a Boolean. And RSP plus 20. So we should be able to just say, add a return value to it of type bool. And this will set that bool. I hope I've coded that right. Which means that we should be able to just go like this. And that should check whether it was successfully set it to 1. And if it did, if it didn't successfully set it to 1, then we wait. And and now I've lost track of where that is. So it's like Futex wait. Futex wait. What are the parameters that we pass in? Oh, it's just arg0, arg1. Need to find where it gets used properly. This is where we were. So the expected value and the timeout. The timeout we're just going to set to 0. And the expected value is the current Futex word. So does that mean that it's also 0? I don't know, I'm a bit confused about this. I don't know if this is right. But the idea is that like, if the mutex is 0, then we set it to 1, which means this passes, and so we should not go to here. If the mutex is already 1, which means that it's locked, then it's false. So then it should go to here, which means that it waits. And it should wait for it to for this to be signaled. In which case, I guess we try again. So maybe it would be 4, actually. We keep trying. And then unlock. We say if, and then we go from 1 to 0. So if the mutex is 1, then we set it to 0. And if that succeeded, if it didn't succeed, it means that it was not locked and there was nothing to do. So we don't do anything. If we did succeed, then it's like a futex. There's futex something else. Here it is, futex wake. And then the number of things that we wake. So futex wake, I think, is 1. Yeah. So operation 1, and we want to wake 1 thread in that case. So it's like this is the expected, whatever that means. This is the count. And this is the timeout. So hopefully that's going to work. I'm really not sure if this is the right value. Everything else makes sense to me. Let's see. So let's take this out and say here's our mutex. We're going to lock it. And then we're going to unlock it. So let's say that's our mutex test, and our mutex test is complete. What happens? Unsupported byte size. I knew there was going to be some sort of problem. So what is it? What's the type node? It's probably nothing, is it? Ah, it's a call. Okay. So probably we just need to get the result. Is there somewhere else that's like that as well? Probably in the 4. Yeah. So then that should not be a call anymore. Hey, mutex test complete. If I just try to unlock it, when it's not locked, that should also work actually. But if I try to lock it twice, oh, okay. That should not work. You know, like this second one should spin, I think, or should wait. So maybe, if we go back to the standard, maybe this guy I got wrong. Should be 1. Mutex test complete. So we take the mutex. If it's 0, we set it to 1. If it's not 0, we wait. So this one should set it to 1, and this one should wait. I think that makes sense to me. Unless our return value is not working correctly. We hard-coded it right. Maybe that's not working. set of 0, RSP plus 20. I don't know if parameters get, in return values, does that memory get initialized to 0? I don't know if it does, actually. That could be an issue. I don't know. What? This is expected value, current mutex word. So if we come in here and this evaluated false, that means that the mutex was 1 because it wasn't 0. So we're expecting it to be 1. Right? This timeout of 0, I think means that it'll just wait indefinitely. So if I just do that and say, basically say it's locked, already locked, and I try to lock it again, like this unlock, I think it's fine that it does just like, if it's already unlocked, then there's nothing to do. I think that's fine. And here, if it's already locked, then we wait. And I don't know why that's an issue. We are copying into 64-bit registers. Well, that's, yeah, but I mean, that's an address, so that should be fine. Why is it putting that into EDI? I guess this code is maybe assuming 32-bit or something, because you would not put an address into a 32-bit register. I don't know what the issue is here. I don't know why this word not be happy or not do what I want. You know, it's like it's trying to lock something that's already locked. And yeah, it could be this. So maybe I can do like a test like if, put it here, if compare exchange mutex then we say locking. Need to wrap it in brackets. Excuse me. I do think I'll fix that up so I don't need to put brackets there. Okay, so we need pointer. Okay, so it's saying that that's true. I think it should not be true. You know, it should be comparing 1 with 0 and seeing that they're not the same and not doing that. Is my understanding. So if I do that, it also says locking. So it's like, doesn't seem to matter what this expected value is. And the parameters do, yes, the return value goes onto the stack, then the parameters. So this one should be further back. The first parameter, second parameter, no, this is the last parameter, the third parameter, second parameter, first parameter, return value. We've got 4 byte increments each time because they're all 4 bytes. Ah, but this is not, this is 8 bytes. So that should be 24. So that should work. That should not say locking. Boom. So it's trying to lock, but it's already 1. But if I do this, yeah, then we work. If we try to do twice, it should, yeah. Okay, so, sorry, that was a bit, I had a bit of trouble trying to figure that out, but yeah, it was because I had my offset wrong here. But I think that's all good. So maybe we can do like do a multi-threading version. So what would that be if we lock and we have a mut func which unlocks. So on the current thread we lock on another thread we unlock, and on this thread we lock again. So we lock, and then it should come, when it gets down to here, it should try to lock again, but it'd be like, well, I can't lock again because it's already locked and I'm just going to wait. But then this other thread should come along and say, okay, I'm going to unlock it for you. And I think that should work. Cannot reference type I32. We don't need to have that there. Okay. So it unlocked. I mean, if we take out this thread, if we never call that thread, the test should never complete. Yeah. But because we call that thread and it does the unlock, then it completes. Okay. Sorry, we dragged on a little bit there because I couldn't figure out that bug for a while. But there, we have semaphores, mutexes, and this is just a bit of a building block, I guess. We have these atomic integers. I'm pretty happy with that. And our threads now take arguments. It's super basic, but it's all we need for now. So I'm pretty happy with that. Okay, thanks for stopping by. Next time, let's make a thread pool. Maybe we can actually distribute stuff across threads. That'd be nice. Ciao for now.